Hello students, welcome back to Modern Physics. In the previous session, we studied the dual nature of light, Planck's hypothesis, the photoelectric effect, the Compton effect, de Broglie's matter waves, Bohr's model, and spectroscopy. In this second part, we will continue with radioactivity, nuclear fission and fusion, the uncertainty principle, Schrodinger's wave equations, Einstein's relativity, semiconductors, lasers, optical fibers, and the many applications of modern physics. Radioactivity is the spontaneous disintegration of unstable atomic nuclei discovered by Henri Becquerel in 1896. It emits three types of radiations: alpha particles, which are helium nuclei, heavy and with low penetration; beta particles, which are electrons or positrons with moderate penetration; gamma rays, which are high energy electromagnetic waves with very high penetration. Radioactivity is a nuclear property and is not affected by temperature, pressure, or chemical changes. The number of undecayed nuclei at time t is given by the decay law, n equals n naught multiplied by e to the power minus lambda t. Here n naught is the initial number of nuclei, lambda is the decay constant, and t is the time dot the activity, which is the rate of disintegration, is given by a equals lambda multiplied by n. Half-life is the time taken for half the nuclei to decay. It is given by t half equals 0.693 upon lambda. The mean life is the average lifetime of nuclei, given by tau equals 1 upon lambda, which also equals 1.44 multiplied by t half. Sir, is half-life different for each element? Yes, exactly. Each radioactive element has its own characteristic half-life, ranging from fractions of a second to millions of years. Radioactivity is very useful in our lives. In medicine, cobalt-60 is used for cancer therapy, and iodine-131 is used as a tracer for thyroid problems. In industry, radioactive isotopes are used for thickness gauges and leak detection. In archaeology, carbon-14 dating helps find the age of fossils. In agriculture, radiation helps create new plant varieties through mutation breeding. The size of a nucleus is related to its mass number. The radius is given by R equals R naught multiplied by a to the power 1 by 3. Here R naught is 1.2 femtometers and a is the mass number. The stability of a nucleus is measured by binding energy, which is given by binding energy equals delta M multiplied by c square. Nuclear fission is the splitting of a heavy nucleus into two smaller nuclei with the release of energy. For example, uranium-235 absorbs a neutron and splits into barium and krypton, releasing about 200 million electron volts of energy. Fission is used in nuclear reactors to produce electricity and, unfortunately, also in atomic bombs. Nuclear fusion is the combination of light nuclei to form a heavier nucleus with huge energy release. For example, deuterium plus tritium gives helium plus a neutron plus 17.6 million electron volts. Fusion powers the sun and stars. Scientists are still working to make controlled fusion possible on Earth for clean energy. Werner Heisenberg proposed the uncertainty principle. It states that it is impossible to measure both the position and momentum of a particle at the same time with complete accuracy. Formula: delta x multiplied by delta p is greater than or equal to h upon 4 pi. This principle is a fundamental feature of quantum mechanics. Erwin Schrödinger developed equations to describe the wave behavior of particles. The time-dependent equation is I bar multiplied by partial derivative of psi with respect to time equals Hamiltonian multiplied by psi. The time-independent equation is minus h bar square upon 2m multiplied by Laplacian of psi plus v psi equals e psi. Here psi is the wave function and it represents the probability distribution of particles. Sir, May I ask, what does psi really mean? Very good question. Psi itself has no direct meaning, but the square of its magnitude gives the probability of finding a particle at a given place. Albert Einstein's special relativity showed that space and time are not absolute but depend on the observer's speed. Important formulas are Lorentz factor gamma equals 1 upon square root of 1 minus v square upon c square. Time dilation T equals gamma multiplied by T naught. Length contraction L equals L naught upon gamma. Mass energy relation E equals mc square. At very high speeds, near the speed of light, Newton's laws no longer hold. We must use relativistic formulas. Momentum P equals gamma m naught v total energy E equals gamma m naught c square. Kinetic energy K equals gamma minus 1 multiplied by m naught c square. These corrections are vital in particle accelerators and GPS satellites. Semiconductors like silicon and germanium are the heart of modern electronics. N-type semiconductors have extra electrons. P-type semiconductors have holes as majority carriers. Devices include diodes, transistors, solar cells, and photodiodes. Without semiconductors, there would be no computers or smartphones. Lasers are light sources based on stimulated emission of radiation. They are monochromatic, coherent, and directional. Applications include surgery, CD players, and communication. Optical fibers transmit light using total internal reflection. Their efficiency is given by numerical aperture, which is Na equals square root of n cos square minus n clad square. They are used in internet cables and medical endoscopy. Modern physics is not just theory, it is everywhere around us. Fraunhofer lines help us know the composition of stars. Raman effect is used to study molecular structures. Zeeman effect reveals magnetic fields. Radioisotopes save lives in medicine and help in archaeology. Semiconductors and lasers run our entire electronics industry. Relativity ensures